Hello, this is the Effects of Mobility on COVID-19 Spread, a project for CS 4641 by Group 17, comprised of Susannah Cole Ham-West, Collin Hubbard, Alex Kelso, and Chris Waid. Here's the agenda for our presentation. We'll start with an introduction leading into the definition of our problem, data collection, then our methods, and wrapping up with our results and conclusions. Let's begin with a general introduction of our topic. In early 2020, as COVID-19 spread, world governments established lockdowns and procedures designed to decrease community transmission of the disease. Consequently, mobility largely decreased across the world. There is believed to be a strong link between mobility and community spread of COVID-19. While data on COVID-19 might not be available for many weeks after infection takes place, multiple sources of mobility data are available with relative immediacy. This project seeks to investigate if it is possible to leverage this time difference to make effective predictions about COVID-19 in the near future.
We decided to do this using neural networks and specifically an LSTM layer. We outlined this in our problem statement where we define that we seek to use mobility data to make predictions of COVID-19 case counts in the near future. It is our goal to evaluate the efficacy of using LSTM, long short-term memory, model to predict COVID-19 case counts. For our data, we needed two data sets. The first data set is the COVID-19 case count data that we got from the CDC website. For this data set, we focused on the date, state, total case counts, as well as new cases for this data set. We also used trip mobility data that we got from the U.S. Department of Transportation website. For this data set, we focused on the date, state, population of people staying at home, as well as the number of trips being taken. We did some initial exploration of this data. As you can see here, we have the population of people staying home, the total number of trips being taken, as well as the new cases of COVID-19 per day. As you can see from these graphs, there seems to be a correlation in the middle months of 2020 especially between a rise in COVID-19 cases, a decrease in the population of people staying home, with an increase in the number of total trips. We will now transition to discuss our methods. We started by cleaning the data, did some feature selection analysis, trained and tested our LSTM, then compared the data with random noise, and finally compared the LSTM with a fully connected layer. To clean our data, we found that the data had the most significant correlation in 2020, as in 2021 with the rollout of the COVID-19 vaccine, there became a compounding factor to the COVID-19 case counts. We also filtered the data to only include data for both data sets at the state level. We then joined the COVID-19 dataset and the trip dataset by both state and day.
Feature selection was performed using Pearson correlation coefficients to see how the different features related to each other. For this heat map, the means of all the mobility features were condensed into one variable, var1. In this heat map, var1 represents the mobility data, and var2 represents new COVID cases. Variables that correlate more strongly to var2 at time t, shown here at the very bottom row, will indicate that they are stronger predictors of the number of new COVID cases and would thus be useful features for our algorithm. The red box in the bottom right indicates that the new COVID case count from 7 days earlier is highly positively correlated with the new COVID case count on day t. The varying shades of blue on the bottom row indicate that the most strongly correlated mobility data lies between 4 and 6 days before the day at which you are predicting new COVID case counts. This is consistent with the medical research on the incubation time period for COVID-19, which is between 4 and 6 days. The data was then used to train an LSTM machine learning model. The LSTM was trained under 3 circumstances. 1, on an individual state's data. 2, on all of the state's data at the same time. And then 3, on random noise. For the training, we used a train test split of 80-20, meaning that we used 80% of the data for training and 20% for testing. Lastly, we created a dense neural network where instead of using an LSTM layer, we used a fully connected layer with a similar number of parameters to the LSTM layer. We ran this model on all 50 states as well to compare it with the results of our LSTM. Now let's take a look at the results so that we can see the accuracy of the model when it's applied to each state individually, then the accuracy of the model when it's applied to all the states' data at the same time. And then we'll compare the effectiveness of our LSTM model compared to a simple neural network. To evaluate the performance of our model, we used mean average percentage error as a metric since root mean squared error was more influenced by large data values, while MAPE is less affected by this due to it being a percentage. As you can see from the graph, the MAPE for each state lies between 1% and 6.5%. When we ran the LSTM with random noise instead of mobility data, this resulted in a much higher error, which means that the mobility data is not equivalent to random noise. The MAPE for the random noise was about 350%, which is significantly higher than the results we got with the mobility data. We also trained and tested the model on all 50 states' data at once with mobility data, which was from 1 week before the reported cases. This performed surprisingly well, but was still worse than just training and testing on a single state. We had to decrease the number of nodes to avoid overfitting, and also included a dropout layer of 40% to further avoid overfitting. Dropout is similar to ridge regression, but is applied for neural networks. Here you can see the MAPE reaches a minimum of about 10%, which is good, but is still not as good as the previous results we shared. We also created a simple neural network where instead of using an LSTM layer, we used a fully connected layer with a similar number of parameters to the LSTM layer. We ran this model on all 50 states as well to compare the two models. It did not perform as well as the LSTM, which makes sense because it is not able to access past data as the LSTM is. The mean absolute percentage error by state ranged from 3% all the way up to 17.5%, whereas for our LSTM model it was much lower, ranging from 1% to 6.5%. Some of the challenges we faced included being limited by the amount of data we had, with only 1 year of data available for a neural network that works well with big data. We would also be interested in further study to see how our results compare with the performance of a simpler regression analysis. Ultimately, however, the LSTM model we created was able to accurately predict case counts for individual states, with states' mean average percentage error ranging from 1% to 6.5%. Merging all of the states' data together performed surprisingly well, with a MAPE of under 10%, but still not as well as just viewing the individual states. This is congruent with intuition, as interactions between individuals in different states are not likely, and analyzing COVID-19 spread in specific regions is easier than analyzing the spread across the entire nation. Further, the model trained on the mobility data performed much better than the model trained on random noise, which is to be expected, and proved that the mobility data is more useful for COVID case prediction than random data. Finally, the value of the LSTM model was proven by comparing its results to the results obtained by training a dense neural network. The memory capability of the LSTM allows it to access past data, resulting in MAPE values state by state that were much lower than those obtained from the simple neural network.
Here you can see the references that we used for this project. This wraps up our presentation. Thank you so much for listening.